Hello everyone, I am Kanjasit Thonglek from Software Design and Analysis Laboratory at Nara Institute of Science and Technology, Japan. Today I would like to present my research about the federated learning of neural network models with heterogeneous structures. In the past decades, if we would like to use the AI on edge device, we still require to transfer the data from edge device to a centralized server, since it requires a huge computing resource for training and inferencing. And then the server will return the inference result to the edge device. For this purpose, the centralized server can gather the data from edge device and update the model frequently, due to it receive the updated data from edge device simultaneously. However, it takes long response and lack of data privacy because users have to transfer their data from edge device to a centralized server. But nowadays, we can deploy AI on edge device because the edge device has more computing power than ever. For this process, it takes a shorter response time than the previous process, and it has a better data privacy because it does not require to transfer the data to the centralized server for training and inferencing. But the main drawback of this process is it cannot update the model on the centralized server from the data that collected at the edge. Therefore, the federated learning has been introduced to address this problem. Federated learning has been introduced by Google in 2016 for computing AI on edge device. They define the local model is a model that deploy on edge device, and the global model is a model that deploy on the centralized server. The federated learning is a method to update the global model using the updated parameter of the local model without transferring the raw data from edge device. So the edge device requires to transfer only the updated parameter for better data privacy. Due to the current technology, we cannot extract the raw data from the model parameter. The federated learning has the main method which called the federated learning algorithm. It aggregates the updated parameter of the local model with the global model. However, the federated learning still requires the model with homogeneous structure. By the global model and the local model must have the same structure. But in the real-world application, we cannot deploy the homogeneous model on every edge device because of the heterogeneity of edge device. Clearly, the edge devices are heterogeneous from many aspects such as storage capacity, computing resource, power consumption, and network bandwidth. Moreover, some edge devices have an accelerator like GPU or graphic processing unit, or TPU, tensor processing unit. From this reason, we cannot deploy the same neural network model to every edge device, since the different neural network model require different hardware specifications for running. For example, the federated learning for heterogeneous model, we deploy the MobileNet on mobile and VG16 on PC. By the size of the MobileNet and VG16 are totally different, which are required different hardware specification of each device. But the existing federated learning can support the neural network model with the homogeneous structure only. Therefore, we propose a method to support this situation. So, we propose the method that enables federated learning to combine the neural network model with heterogeneous structure. First, we apply the federated averaging with the state-of-the-art of the federated learning algorithm to update the global model using the updated parameter from the local model, which has a homogeneous structure. After we update the model which has homogeneous structure, we apply weight average assembling to combine the neural network model which has heterogeneous structure. The weight average assembling is a simple and efficient assembling method to combine the model with heterogeneous structures. We use this equation to evaluate the weight for each output class of each model with heterogeneous structure. We define y is the final output vector, x is the input data, n is the number of model, and mi of x be the prediction of x using model I, and alpha I is the weight vector for model I. The alpha I is determined by applying the optimization algorithm to the optimized weight for each output class of each model to maximize the accuracy. In this work, the proposed method applies 6 backblock optimization algorithms to optimize the weight. First one is GS or grid search. Second one is RS or random search. The third one is the PSO or particle swarm optimization. The fourth one is the BS or Bayesian search. The fifth one is SMAC or sequential model based algorithm configuration. And the sixth one is the TPE or tree present estimator. We set up 3 experimental setups A, B, C to evaluate the proposed method. For every experimental setup, have the same total number of edge device is 1200 devices. For setup A, we deploy 2 models, MobileNet and DensNet 169. For the setup B, we deploy 3 models, MobileNet, DensNet 169 and LessNet 50. And for the last setup C, we deploy 4 models, MobileNet, DensNet 169, LessNet 50 and VG16 among the edge device. By the difference, experimental setup had the difference number of device per model and difference number of image per model, like the table on this slide. We use for the state-of-the-art model for image classification tasks. The first one is the MobileNet, second one is the DensNet 169, and the third one is the LessNet 50, and the last one is the VG16. From the left figure, show you that the different neural network model require the different storage size, and also from the right figure, show you that the different neural network model require the different number of floating point operation. This slide confirms that the different neural network model require the different hardware specification for running. Furthermore, for every experimental setup is executed with the most 4 popular image classification datasets. For the first one is the Cipher10, second one is Cipher 100, and the third one is the ImageNet, and the last one is the R Cellular. This slide shows you the example of optimized weight for the output class of each model. In the experimental setup C, we Cipher 10 datasets using TPE optimization. For the same output class, model with the darker cell are weight heavier than the model with the lighter cell. Taking the egg output class as an example, MobileNet has the highest weight, while the DensNet 169 has the lowest weight. This suggests that the MobileNet is able to identify the egg class more accurately than DensNet 169. In this manner, models that achieve the higher accuracy on particular class will have higher weight assigned to them after the weight optimization. This slide shows you the improvement of model accuracy during applying the optimization algorithm in the experimental setup A with R Cellular dataset. Before applying the proposed method, the accuracy of the combined model was around 63%. After performing 50 optimization trials, TPE achieved the highest accuracy around 75%, while the GS or grid search produced the lowest accuracy around 70%. However, the different accuracy are not that significant. Similar results were observed with the other experimental setup B and C. We compare the accuracy and runtime required for tuning the weight with each optimization algorithm in experimental setup A with our cellular dataset. Evidently, optimization methods that achieve higher accuracy require longer runtime. TPE was slowest, taking more than 3 hours to complete the optimization, whereas the GS was the fastest, only taking 17 minutes. We also measured the runtime using experimental setup B and C, and we observed the same thing. Moreover, we also found out that the runtime increased with the number of models and the number of output class of each model. For the conclusion of this work, we proposed a novel method to ensemble the neural network model with heterogeneous structure for federated learning. Moreover, we compared 6 optimization algorithms to tune the weight for each output class of each model, and found out that the TPE was able to achieve the highest accuracy. For future work, we will investigate the other parameter optimization method and federated learning algorithm. Any questions are welcome. If you would like to discuss about this work in more detail, please don't hesitate to contact me by this email on this slide. Thank you very much for your attention.